Hello everyone. So today we're going to find a potential function f that goes from R2 to R, for which the vector field capital F is equal to the gradient of f, okay? Where capital F, the vector field capital F, equals 2xy minus 7x, that's your first component, comma, x squared minus e to the y, that's your second component. So yeah, it's f, lowercase f, is called a potential function because the gradient of f is equal to capital F vector field. So in order for us to find the potential function, we have to, first of all, let's go back to what it means to be a gradient. So a gradient is when you take the partial derivatives of your function with respect to x, y, z, well, whatever. And this here is just going to be with respect to x and y. And we're going to place those and set them equal to my components for my vector field f. So again, the gradient of lowercase f equals fx, fy, and that's just by definition. And if you told me, well, this gradient has to equal the vector field capital F, then it's got to be the case that each component each like component equals each other. So fx has to equal the x component 2xy minus 7x, and fy's got to equal the component x squared minus e to the y. That must occur here because that's what it means for two vectors to equal each other, is if the components are equal to each other. So the question is, well, from here, how do I get f of x, y, or potential function? A couple ways of doing that. Primarily, you're going to be integrating. You're going to go ahead and either find the integral of fx dx, or you're going to find the integral or antiderivative of fy dy. Either one will work out here. I'm going to go with the dx one. Again, doesn't matter which one you pick. Don't get me wrong, sometimes the computation might be a little longer for one, but it works out. So I'm going to integrate 2xy minus 7x dx here. And if we went ahead and integrated with respect to x, y will be treated as a constant. So this is going to be x squared y minus 7 halves x squared plus g of y, okay, in red here. Now, why g of y? Because we're integrating with respect to x, so anything that is not x is like a constant for us. So I'd be adding, normally when we find the antiderivative of something, yeah, you include a constant. But in this case, the constant is replaced by a whole function with respect to y. Because if you were to, how do you check your work? You take the derivative of what you have or what you claim is the answer with respect to x. That's how you find, that's how you check an antiderivative. Well, this g of y part would just equal 0 because g of y is just a function of y. All right, so, and my big point here is that you'll always something with that respect when you're integrating a two-variable function in the sense that you're going to add a function of y, you're going to add a function of x, either one, it depends. In this case, it's you add a function of y. Over here, it's a function of x when you're integrating fy dy. Okay, so we have that our potential function looks like x squared y minus 7 halves x squared plus g of y. But we need to find the g of y. That's the next part of the problem. Now, we claim that this is what the potential function is when we solved. Let me just rewrite it here. And if I were to take the partial derivative of this with respect to y, you would get fy equals x squared plus g prime of y. Okay, that would be our claim. That would be the partial derivative with respect to y. Well, that right there has to equal x squared minus e to the y. Okay. So once again, that has to equal x squared minus e to the y because of what we were saying earlier. The fy, which was the second component of the gradient, has to equal the second component of the vector field that we're claiming it's equal to. So fy has got to equal x squared minus e to the y. Okay. And in this part, let me just stop for a second and speak about something that confuses people with this step. So a lot of people will ask me, how is it that you had to take the derivative of what you just integrated here? Okay, they'll say like, well, it looks like we have it already. What else do we need to do? As I said, we need to find g of y. And the only other piece of information that I have is the partial derivative of y, what it's supposed to be, which is that x squared minus e to the y. So if I claim my function is given as, have it in my box, well, the partial derivative of that has to equal the partial derivative of what we're claiming here. So that's why I'm setting these equal to each other. So you get your function, you integrate it, and then you find the function at the end, which you're looking for g of y or h of x, whatever, by taking the partial derivative of your function with respect to what you didn't work with, which in this case was y, and then you set those two equations equal to each other. In this case, you'd get g prime of y equals minus e to the y, and if you integrated, you would get minus e to the y plus some constant. So your potential function, we say, has to look like x squared y minus 7 halves x squared minus e to the y plus c. And yeah, c is some arbitrary constant here. All right, now this can also work for, can find a potential function for something that goes from R3 to R. That in itself is very similar to what we're doing, but there's a couple things that we need to speak about, which I won't talk about here because it's going to take a lot more time than it needs to. But again, yeah, so that's just to recap what we did here. When you're looking for a potential function, you're setting the components of the vector field f equal to either fx or fy, and you choose one to integrate. It's up to you. And once you integrate, you need to find what the function g of y is, or h of x, or whatever number you want to call it. And you do that by taking your result that you just got after integrating and taking the derivative with respect to the variable that you didn't integrate with respect to. In this case, it was like we integrated with respect to x, so I take it with respect to y. And yeah, you try to, you have an equation which you try to solve, and that's it. And that is your potential function. Okay. All right. Well, thank you for your time.